This is a screencast for section 9.45A2. We already looked at a couple of basic series tests to see whether the series converged or diverged. The nth term test for divergence, and then the p-series test. Now we're going to look at another test called the direct comparison test. By the way, there's going to be about 9 tests in this unit, in these 945 units here. So hang on, we got a few more to go. The direct comparison test is exactly that. We're going to directly compare the series we're trying to test to another series that we're familiar with. First of all, we can have to have a series with no negative terms, and that would be an obvious negative term in terms of an alternating series, which you will see in section B. What the direct comparison test says is that if you know of a series, let's call it C sub n, that converges, that gets small enough, fast enough, so that the sum is equal to a number instead of infinity, the sum of that series, and the one we're testing has values even smaller than that, it will also converge. The one we're testing will also converge. Now the reverse is true for divergent series. If we know a divergent series and the one we're testing has even bigger terms than that, then we know that the one that we're testing is divergent. Now we have a couple of good series to use in direct comparison test, namely a geometric series or a p-series. And why those are so good to compare is because geometric's pretty easy, that as long as your r value, you have your r to the n, and as long as your r value is smaller than 1, you have a convergent series. And then a p-series test, 1 over n to the p, as long as p is greater than 1, you have a convergent series. So if our series is a good comparison to a geometric or p-series, that's easy. We're actually going to do a different scenario here. In example 2, we're going to prove convergence by comparison. And I'm looking at this and I don't really see a geometric or a p-series situation here because n is in both the numerator and denominator, but not an exponent in both. So I have to think outside of that box of geometric or p-series. So let's take a look. First of all, each of these terms are greater than 0. I don't see any negatives in my series representation here. Now, I'm going to look at a bigger denominator. So like n factorial squared, smaller denominator. N factorial squared is humongous. So these terms are pretty small because we're dividing by this humongous number. Now, if we divide by less of a value, so just n factorial, not n factorial squared, these terms are going to be bigger, but this is starting to look familiar to me. This looks very much like the Taylor series for e to the x squared. So, which I know converges for all x, and that's back from section 9.2, the representation of Taylor series for these known polynomials, or not polynomial, functions. So now, since this function that I know, the Taylor series for e to the x squared, converges for all real numbers, because it's the Taylor series for e to the x squared, by the direct comparison test, the one that we're testing also converges for all real numbers. So basically, we've laid out that our series is always positive and it's less than this convergent series. So this convergent series is going to sandwich our series between 0 and it. So it also converges. The now try problem, example 3, says use the comparison test, to show that the series converges for all x. Now, you actually won't be told what test to use, so that's why I kind of gave you this nice big chart here so you can become more familiar with the tests and how they work and their rules and all that. So here we've got this series that looks very complicated. There are no negatives in it, so it's always going to be positive. Now, if I start to simplify that denominator a little bit, I'm seeing that whole n factorial on the bottom. So I took out the 2, I took out the plus 1 because those are making this denominator bigger, but they're not really significant in terms of how large each term of these series are going to be. Multiplying by 2 and adding 1 is less significant for n large. So now just looking at a denominator of n factorial, these values are going to be bigger than these values, but this term, the series that I'm starting to compare our questionable series to, looks familiar to me. That is also the Taylor series for e to the now x cubed, also from section 9.2. So since the series I'm comparing it to converges for all x because it's the Taylor series for e to the x cubed, by the direct comparison test, and I can use that because my values are all positive and I know this series converges, the series I'm testing converges for all real numbers. So again, this is kind of how you have to lay that out. Show that you have positive terms, show that they are less than something you know. Now since this one converges, you can use direct comparison test. So you're kind of setting up the direct comparison test here, and then you're stating why the direct comparison test works.